We're going to take a look at nuclear reactions. It's section 25.3 in your book. This is the last section we're going to do before the next test. The next test is going to be everything we've done in chapter... Yes. Everything we've done through, section 25.3. What we're going to do after this for the next sections is jump back and take a look at fluid mechanics, which is an earlier chapter in your book. I think it's chapter 9 or 8. I forget which one. Anyhow, so the three objectives for this topic. First, we're going to talk about and distinguish between nuclear fusion and fission. They're two different processes. Second, we're going to explain how a chain reaction is utilized by nuclear reactors. Processes? The plural of process? Processes. Yeah. I've always said processes, and so have all my professors.
How is it spelled? I feel like that's spelled the same.
Yeah, it's the same spelling. It's like, I think it's a different pronunciation. Yeah.
I just never heard of it.
Anyhow. Next. Guys, stop. Next, we're going to compare fission and fusion reactors and look at the difference in the reactors themselves. So first, to start, we're going to define the term nuclear reaction. A nuclear reaction is defined as any process that involves a change in the nucleus of an atom. Again, a nuclear reaction. Any process that involves a change in the nucleus of an atom. This is very different than electrons jumping from one orbit to another, or electrons moving from one particle to another and causing one of them to be charged. This is a change inside the nucleus. So remember from last class we talked about the strong force that holds the nucleus together. When there's a change inside there, some energy has to get released. So there is a lot of difference here between this and simply electrons moving from orbit shells. Okay? Nuclear reactions release a lot of energy, which is why fission and fusion are something that is so desired to harness the power of, right? That's what the ultimate goal is.
Two things. First, so a nuclear reactor is something that
controls fusion or fission. Yep.
And also, there's a question in the text. We're talking about the Rutherford model. And it discusses how a scientific maximum or something like that. So the radiation is caused through the acceleration of electrons. Is that still true?
Say it one more time, slowly.
So we're talking about the Rutherford model and why it discusses things are unstable, and it says that because he says that electrons go through a certain acceleration while they're moving.
Yeah, because the electrons are kept in a circular orbit due to the attraction between the negative and positive, the positive center and the negative electrons. So that's keeping it in orbit, the electric force there. That electric force is in circular motion, which means it must have centripetal acceleration.
And that acceleration causes radiation.
Yeah, that acceleration is causing it to want to almost, just kind of dive into the nucleus. But what's keeping things apart, keeping things into control, is that strong force there.
So an actual decrease where they, over time,
they want to.
Orbits will want to because they're all negatives.
And they're all positive.
So a nuclear bomb, what causes the radiation is then
a nuclear bomb is not that at all. A nuclear bomb is what we're going to talk about today. And we'll get to it. But it's not what you're thinking there.
I mean, I know nuclear bombs when they get two atoms collide.
They look like a chain reaction.
Yeah.
Can you hold off for a little before I don't want to I'm reading the guy into it again. Let me explain fusion and fission, and I promise you it'll come along with it, okay? But you're at the end of the class, and I don't want to just give that away before we get to it. It's like giving the end of the movie, right? Before you see the movie? That would be the equivalent. I'm just saying. Anyhow. In the example you see here, take a look. First, Paul, come on. It says helium-2,4. That means that there's 2 protons and a total of 4 nucleons. See, helium-2,4. Again, the 4 represents that there's a total of 4 nucleons. So that means there must be 2 protons and 2 neutrons in helium. In nitrogen, there's 7 protons, because you see the 7 there. And then the other 7 that gave you the 14 means there's 7 neutrons. But look at the end now. At the end here, or sorry, not the end, at the intermediate phase, this helium and nitrogen, it's really a nitrogen atom, and it's being bombarded by helium. Helium in the form 2,4 is called an alpha particle. It's a type of radiation. So an alpha particle bombards the nitrogen atom. It attaches to it and becomes fluorine. And take a look at your numbers. You can see the balances. You have 9 and you have 18. So it becomes fluorine, but fluorine 918 is unstable. So what happens then is that wants to disintegrate. Okay? And it disintegrates into two things, into oxygen and into hydrogen. So here we have an example, hydrogen 1,1. What's hydrogen 1,1? What is it, Joseph? It's just a proton, positive charge, hydrogen 1,1. So this is releasing a proton as a result of some radioactive process. So it's all right, guys. Trust me, we're not going to balance numbers, we're thinking theory. Here's what's happening. Just listen as you watch. Nitrogen atom is hanging out here. It gets bombarded by a helium atom, by an alpha particle, which causes it to become fluorine. Look at the numbers, just add them together. It becomes a new particle. But fluorine 918 is unstable. Unstable elements want to disintegrate into stable forms. Oxygen 817 is stable. A proton by itself is stable, so it breaks up into those two, becoming stable.
Does that release the energy?
You need to ask once at a time, guys. You can't all ask once. Come on. Olivia, in first.
So, does that, that split, does that make the energy?
Yeah, there's going to be a release of energy as well with this. Absolutely. For this to go together and separate, there has to be some sort of delta energy. And we'll talk about that in fusion and fission. This is just an example.
Why is it unstable?
Remember we talked about the number of neutrons not being enough for the number of protons, making it unstable? That's one of the reasons in this case. Okay? Jeff?
I'm kind of along with that question. I'm not understanding, let's say fluoride is the 18 over 9. I mean, 18 and 9.
Yeah, we're not going into why these ones are unstable. We're going into the processes that are
But
happening.
then why, can we also know why, though, that hydrogen is stable because they both
It's a proton. A proton is stable by itself, yeah.
Oh.
It only has a positive charge, but it's not. A proton has no desire to split up into further elements.
17.8 though, that seems like a high number.
But in this case, look, wouldn't there be one more neutron than protons? Look at oxygen, everybody. There's 8 protons, but there must be 9 neutrons to get to 17, right? And we want more neutrons to be stable. We said that last class. You need to recall that previous knowledge. Okay?
So it's not stable if they have the same amount?
It is sometimes, but generally speaking, you want to have more neutrons. This happens to be an example of one that is not stable. Okay? We don't want to generalize and say that it's not if they're balanced. Okay?
But why is it oxygen and hydrogen and not like 2 other atoms that add to fluorine?
Because oxygen is not being bombarded with hydrogen. Here's what's happening. You literally, I'll draw a diagram if it helps. You've got this nitrogen atom here. You've got this alpha particle here. The alpha particle hits the nitrogen atom, making fluorine. Then fluorine breaks up into oxygen and some positive proton going off into
But why does
space.
it break up to something else other than oxygen? It just, you don't need
Oxygen happens to be the most stable thing nearby fluorine, so it's picking that. It wants to move down a little bit or change its energy level, but not too much. The rest of that you have to go into a little more like quantum physics and chemistry. Okay? All right, let's take a look at the process of fission. Fission is the following. It's a nuclear reaction where a nucleus splits. You need to know the difference because you're going to hear fusion in a minute. Fission splits. Here's how I remember it. Ready? Fission has more S's than fusion. Fission has 2 S's, right? Remember the extra S stands for splits. Easy way to remember it. It does work though. Fusion will have 1 S in it. Fission will have 2 S's. That extra S from fission, think about splits, okay? Yeah.
So fission sounds like division.
Oh, there we go. Perfect. Fission sounds like division. And division means splits. Good, Stash. Thank you. Did you hear that one before or did you just think of that? Just thought of that? Yeah, I thought of the other one. I was like, oh, it works, but that works perfectly. Now, 3 things. 3 things to write down. First, since it's a process of splitting, this only occurs for heavy nuclei. Only occurs for heavy nuclei. That's the first thing. Specifically, and you can put this in parentheses, atomic number is greater than 58. Okay, that's our like transition phase there, or transition point.
Wait, fission?
So fission occurs, again, for only heavy nuclei, and traditionally, for atomic numbers greater than 58. I think lead is 58, I'm not sure. It is a heavy number, yeah. It's a large. Oh, the elements. Look at the elements. What do they range from? From 1 to, what's the highest element?
178.
Yeah, so like above 58 are considered heavy. That's what it's saying here, okay? Second, in the process of splitting up, the nucleus releases energy. The nucleus releases energy. That's the second point. So the first point was that it's a heavy nuclei, specifically greater than 58. The second point is that in the process, the nucleus releases energy. Third, and this is the interesting part, because this is going to be a major difference with fusion and fission. Third, the byproducts, meaning the stuff that it releases, the kind of energy, can occur as photons, protons, and neutrons. Again, some of the common byproducts are photons, protons, and neutrons. We've talked about all three of those. Okay, photons are light energy, protons are the hydrogen atom by itself, and neutrons are neutral particles. Now, an example of this that I'd like you to write down is uranium. And you've all heard of uranium before, and you always have people think uranium, right away you think radioactive or bombs, right? Uranium. So, here's the process of uranium undergoing some sort of forced fission. Shh, guys, listen, stop talking.
Wait, so is that if you want to like deactivate?
If you're going to walk out and come back in, he's going to start talking. People aren't going to be able to leave anymore. We need to focus. Just because someone walks in doesn't mean begin talking again.
If you want to use fission on it, you make it less powerful.
What do you mean?
Like uranium? Oh, you make it more powerful?
So what you're doing to the uranium is you're firing a neutron at the uranium.
Oh!
And that neutron is causing it to become an unstable state, and then that will break up.
And then explode.
Okay?
Because it's so
Let me write the equation down, and it'll make a lot of sense.
Because it's so concentrated, right? That once it's released, the volume is released.
No, it's because I'll explain in a minute. We'll talk about why it's such a process like that. Hold on, Jeff. You're jumping ahead again. Okay? So imagine a neutron. It's not complicated because I'm not asking you to do any math. I'm just telling you theory. So all you need to do is to understand what's happening. So a neutron, you can literally see this, right? A neutron is fired at a cell of uranium or some atom of uranium, which causes the uranium to become 98-236, okay, which happens to be one of the radioactive unstable forms of uranium. Now, so one neutron, you got to come closer if you can't see, Jeff. This is pretty big. I'm right here. One neutron is fired at uranium 235-98. That gets
So you just add one.
that gets into an unstable state. Now, after it becomes unstable, it wants to break up further. And these are just examples. You don't need to have these memorized. It breaks up actually into barium, 140-56 in this case, and krypton.
Oh, so Superman.
Okay? But you know what else it does is this. It releases 3 more neutrons in the process. And you can add up the numbers, please. Add up all the superscripts, add up all the subscripts. They'll match up. So again, you've got 140 as a mass from barium, 93, and then the 3 neutrons are 3 masses.
That 3 means 3 neutrons?
Yeah, so there's a 3 in front of the neutrons. It's like a coefficient. There are 3 neutrons. This is what I'm talking about. It's not stoichiometry. It's easy balancing of numbers. You have like no math involved.
Easy for you to say.
Fernando, honestly, you're adding. Look, add those, and then add these 3, and you'll see a balance. This needs to be a 3.
Know which ones it breaks out to.
You don't have to. Again, I'm giving examples just to talk. Theory. It's all theory. We're not getting into the math here. Now, next. Next. Here's what's happening. And this is what we want to think about. This process to continue. Here's the process you're going to see on the right. If you can't see, then you need to either squint or move up. Please, you need to see this. So, you've got, stay with me please, stay with me. You've got a neutron right here, I'm going to circle it as we go through it, that hits uranium. Now, it causes uranium to break up into krypton and barium. But it also gives off 3 neutrons in the process. Stay with me please. Those 3 neutrons then hit the uranium that's next to it. Because uranium is a big block of uranium, right? It's a whole block of it. So it starts a chain reaction, hits the next uranium particle, which then gives off, again, more different isotopes. This time bromine. Okay, here's more krypton, here's more barium. Here's, I think RB is rubium? Right, rubidium? I forget which the name. CS I know is cesium. Anyhow, this is what's happening though. Every time this process undergoes, it releases more neutrons, which hits more uranium particles. So it's a chain reaction that happens at some exponential decay model. Yes. That's why you've heard of half-life before. It's giving off a certain amount of radiation, giving off energy in the form of fission. Okay, giving off in the form of fission, and it's a chain reaction. Now, some interesting facts about this. Interesting facts. The energy in 1 kilogram of this, you should write these. The energy in 1 kilogram of this would be equivalent to 20,000 tons of dynamite. 1 kilogram, one little bit about this big, would be the equivalent of 20,000 tons of dynamite. Okay? Think about what that would do. They used to use dynamite to blow, holes in the side of mountains to make tunnels. That would blow a mountain to bits. 20,000 tons of dynamite.
To set off that much uranium, you need like a bomb.
And that's what they ended up. That's what they ended up using in one of the original bombs, the atom bomb. Okay, so the atom bomb, yes, the atom bomb, okay, was first called the nuclear bomb, and it was just uncontrolled fission. That's what was happening in the first original atom bomb. Okay, so it starts a chain reaction, and a kilogram of this would do a lot of damage, and that's the idea there. Now, today's nuclear reactors are controlled fission. That's what's happening. Okay? It's controlled fission. And we'll talk about later that fusion doesn't actually work right now. It's tough to harness or control fusion. But fission is working. But that's what today's reactors are. Controlled fission. It's a self-sustaining process. If you have a certain amount of this material, it will continue to sustain its own reaction. And it's controlled. That controlled reaction produces steam in the water that's being controlled in. That steam turns a turbine. That turbine uses that mechanical energy as a generator to generate electrical energy. Okay? Dams take mechanical energy of water that turn this turnstile and create electrical energy. But those steam coming from nuclear reaction is incredibly much stronger. And you only have to use a little bit of it to get a big reaction for a long period of time. Exactly.
So basically,
questions?
So every time these Greenpeace makes a video like a nuclear factory, it's just steam coming out. It's not really like anything toxic.
Well, some of the byproducts could be toxic, and that's what they talk about, like what they do with the waste. And that's where you take like a life cycle analysis class in college. If you go and study engineering, life cycle analysis, I took in grad school, it talks about the processes that undergo from birth to death and beyond. So what happens to create this? What are the byproducts throughout the process? What do you do afterward? What do you do with those uranium cores that are depleted? How are those deposited, right? So that's some of the issues they're having right now. Okay, that's the stuff you have to consider this, and that's your ethics, right? So you take those ethics classes in between.
Yeah, well, France is 95% nuclear, so it's like...
Say again?
France's energy is 95% nuclear.
Okay.
So
Yeah, it's really interesting stuff, isn't it? All right, let's take a look at fusion. Fusion. It's It's a nuclear reaction where two or more nuclei combine.
Fusion.
And anybody, this is a terrible example, but I know you don't have to raise your hand if you're embarrassed, but who watched before Dragon Ball Z? Anybody when they were a kid watching?
Dragon Ball Z is my
Alright.
favorite. I still
So,
watch it.
I know, I wouldn't be
It's my
embarrassed.
whole
I watched it when I was a kid, I'm not going to lie. It was out when I was
It's
a
the whole
kid.
page of my
So anyway, anybody remember the term fusion?
Yeah.
With Vegeta and
of course.
Goku?
Of course. How did I not?
So, in the show, the two warriors fuse together to become Gogeta or Vegito. They call them either one. And fusion is when two. Yes. Or the earring thing. So,
my show.
I know, it's a great show.
I
Anyhow,
wish you could watch all the episodes for free.
yeah,
You're way too enthused.
it's a great show. Listen, guys, if you have like a lot of time and
Which I do.
off the record in college, you have more time in your hands. That's when I watch.
Okay, I'm not gonna be watching it.
During, like, downtime?
It's gonna be for free.
No, you watched it. I watched it on my own, first of all. But like downtime, I would like watch. They're like 20-minute episodes. I watched it a quick episode while I did
worst
some
thing
work.
about it is that it always ends in a cliffhanger every
Yeah.
single season.
I can't stop watching it.
Can't stop.
You watch one and you watch 50 episodes.
It's like 24, you know?
Now the funny part is that even the series so like they're miniseries, you realize, right? They're little chapters in a book, in a manga. Even those are cliffhangers to what about it. So it's like impossible, I know. Alright. Anyway,
And
sorry.
the one battle is like 15 episodes.
It's true. So, some fun facts or some interesting things.
He gets me. What the 24 came clip.
Light nuclei, yes, 24. I'll tell you guys, I watched 24 when I was sick. I had mono in high school. You know what mono is? Okay, stop. So, listen. So in high school, I was out for 3 weeks of school.
Did you watch all 24?
I watched an entire season in an 18-hour sitting. In one 18-hour sitting, I watched an entire season
Wait, so you
of
went- I didn't know
24.
episode.
All 24 through. Yeah. And at this point, my dad owns a deli, so like in the morning, I remember I like went and got breakfast, and then I remember my dad was coming over at 3. I'm like, can you bring me a sandwich? So like I didn't even stop for food. I was eating right through it. I watched 18 hours straight through it.
Wait, the only first two.
I was sick with mono. You know what? I had to get like a tutor for each class for those 3 weeks. And they would come over for like an hour and teach me the whole week of physics, and then I'd be done for that whole week, and it was great. When I was out, I was like, oh, I loved it. So I had time for it now. But no, you know, in college there's going to be classes. There's going to be classes where you have to put a ton of work in, and there's going to be ones you have to be like, all right, this is not that bad. When I took some class in college that I knew from high school or I was good at, I could read the book, that's fine. But then other ones, I had to really do a lot of work. It just depends. Everybody's different. Now, some fun facts. Light nuclei. Nuclei under atomic number 58. Under atomic number 58. Okay, so it's the opposite there. 58 is like the boundary. I don't know which that one works with. Second fun fact. A breaking point. It's a critical point. Yes. Yeah, very good. Critical point. The
atomic number is under 58?
Yeah, so remember the other one was above 58? These are like particles under 58.
Is 58 like the odd man out that's never included?
That's what I said. I don't know. Does 58 undergo fission or fusion? I gotta look that up. The nucleus in this process releases even more energy. Even more energy. Okay? The byproducts include particles such as gamma rays, positrons, P-O-S-I, positrons, P-O-S-I-T-R-O-N-S. So gamma rays, positrons, and neutrinos. Okay? Yeah, so if you were, you know, you make some up. If you were, they discovered it.
It's not true. Someone made it. Nothing discovered and on top of it.
The name, of course. The name, yes. But they were discovered.
Have name tags on them.
So, the idea here, okay, the idea here is the principle that created the first hydrogen bomb. And I'm going to give you an example. Okay, give you an example of the process that it undergoes. Okay, this is the example the first hydrogen bomb. It was really called a fusion bomb, but it was later called the hydrogen bomb because of what happens. And here's what happens. One sec, please. We have two different helium atoms that are clearly unstable. Take a look. Both of these would have more protons than they want, right? This is 2 protons and 1 neutron. 2 protons and 1 neutron. So it's got an abundance of protons. So this is going to be an unstable reaction. The result of this is a stable form of helium, but a byproduct. And the byproduct is 2 hydrogen atoms.
Wouldn't that be?
Okay? Take a look at the numbers.
Yeah.
Okay? So 2 unstable heliums combine to make 1 helium atom that is stable, giving off hydrogen. Thus, the hydrogen bomb. So the name came from here, okay?
But it's also giving off helium.
What happened?
Helium.
Because the helium is not what affects it. The energy comes from the hydrogen bomb, hydrogen part.
This is an example.
This is an example of fusion, yeah. And this is what it's called is the following. It's an uncontrolled thermonuclear fusion reaction.
How are people able to control what atoms do?
Oh, it's uncontrolled, this one.
So uncontrolled thermonuclear reaction.
Nuclear.
I know, but how do they put this all into a bomb?
You gotta learn how to
They become very smart and become like quantum physicists and stuff and learn about it. I mean, at one point in time, right, it was promoted in the U.S. as a means of winning a war. And now it's like, you don't want people to know how to do this anymore, right? So it's funny how the world changes as time changes. I mean, if you started looking up how to make like certain bombs online, you would definitely get flagged, for sure. I guarantee you'd get flagged. Guaranteed. Flag means you're put on a database somewhere in the FBI or CIA or something where it said this person looked this up one time. Let's keep an eye on him or her.
I'm so gonna do that.
I mean, think about it, right? Well, guys, I mean, it makes sense though if you think about it. People that are physicists around the world, I guarantee you some of the top physicists, they are probably guarded whether they know it or not. Because think about it. If somebody took hostage a physicist that knew how to make something like this and really create it, the potential, the worth of that person could be sold on like the black market in other countries and stuff. So I guarantee you that these people are monitored in general.
I'm a recent citizen, so I do like.
You see this in movies. They always steal or hijack some physicist and then they make a bomb out of it, you know?
That's the plot of Mr. Al's protected.
Yeah, what is it? Dark Knight Rises?
Yeah.
So are you flagged? You think?
No.
Yeah, you're
I have no idea how to do this stuff. I didn't study
You watch
this.
Dragon Ball Z and you probably looked up how to make bombs. You're 100% flagged.
No, not me. Now, next. We're almost done. Fusion reactors. Focus. First of all, there's a great desire. Jeff, you need to get water. You need to get water. It's like really loud. I'm not trying to be rude, but I'm being honest. All right. You're not going to miss much yet. First, there's a great desire to harness the energy in a fusion reaction. Okay, but again, this currently is not being done. Second, an example of fusion that's around you all the time is the sun. Again, an example of fusion with helium atoms combined to make another helium atom and byproduct of hydrogen is the sun.
So the sun, what are the products that the sun combines with?
The sun gives off other products as well. So there's some.
What does it combine with?
What do you mean?
The fuse.
It's mainly helium.
The sun is an example.
The sun is an example of fusion, absolutely. It's like fusion bombs going on over and off again. But it's helium that's reacting, but it gives off several byproducts.
So what's
Okay?
the definition of fusion reactors?
I gave you the definition of fusion. It's when 2 or more nuclei combine.
Fusion reactors.
There is no definition. I'm talking about fusion reactors. Okay? So again, there's a great desire because there's a lot of energy, but it has not been created. The sun is an example. For example, next. For example, The byproduct of a lot of fusion reactions is hydrogen, right? So, water has a lot of hydrogen in it. If you could find ways to cause hydrogen to be released in its form, you could talk about fusion using water. Okay, one of its primary fuel sources of fusion will be water, and the equivalent of 1 gallon of water would produce 300 gallons of the energy of gasoline. Think about that for a second. You fill up your car, you put in what? 14 gallons of gas, and that costs you $50, $70, $80 depending on the car you have. Now, 1 gallon of water would produce the equivalent of 300 gallons of gas as energy. So it'd be like filling up your tank.
300?
300 gallons. It'd be like filling up your tank about 20 times. 1 gallon of water in your tank would be the equivalent of filling up your gas tank. What did I just say? 300. Not 300 times. 20 times. Sorry. 300 gallons of gas, which is 20 times. 20 times 15 is 300. So imagine you put a gallon of water in your car, and that's the same as filling up your car 20 times with gas. That pretty much lasts you a year. Most people fill up their gas tank every 2 weeks. So that means that lasts you 40 weeks. 1 gallon of water would last you 40 weeks in a car, if this could be controlled. So think about that. Think about the potential that is existing there. That's why all this funding goes into this technology. That's why people are currently trying to do this more and more. But right now it has not been that successful that it can be.
They know that 100.
That's the equivalent of how much energy is in water if able to be controlled as a fusion reaction. But they know on a small scale, Jeff, they can do it. Guys, they can take 1 atom or 1 molecule of water and split it and harness the energy of that fusion reaction. So what they're trying to say is, imagine if you had this much. They were not able to do it yet, though. Possibly, I'm guessing that's what is happening. Yeah, but they're not harnessing all the energy, and there's a lot of other byproducts. They're not doing it as efficiently as they'd like to, but theoretically, the idea is that it would be the equivalent of 300 gallons of gas.
So, 2 things. Ideally, if we can do this process, that would save like the lack of gas that we're having, and also would like substitute all those what's it called, like natural fossil fuels.
Yes. Coal would no longer exist, all that kind of stuff.
Is quantum physics a hard class?
I never took it.
Probably.
No. I studied mechanical. If you study chemical engineering, you'll take like more subatomic classes like chemistry and orgo and all that stuff. Maybe quantum physics, but quantum physics you usually study like physics majors or an engineer maybe that is a physics minor. I had a math minor though. I took more math classes. The last thing. The interesting fact is that there are very few radioactive byproducts. So this would be a clean source of energy. If able to be harnessed, it would be a clean source of energy. There are very few radioactive byproducts. There was a video that I wanted to watch, and it's about 8 minutes long. Unfortunately, we're out of time. We have 3 minutes. I can start it. It does a phenomenal job simplifying these processes. It's literally about 7.5. I want you to watch the first 7.5 minutes only, and it really does a phenomenal job. Now, where is that video located? If you click on the notes, who's got the iPad up right now? Go to the next page. Go to the next page of your notes. Wherever I have the notes loaded. There's a link there. It says watch until 7 minutes 30 seconds. If you open that on your computer probably, you can click on that link. I don't know if you can select a link in Notability. That's all the issue with Notability.
What happens if you watch?
So you have to open it on your computer. I got to figure out how to change that.
What happens if you watch?
If you load it on Moodle, if you load the PDF on Moodle, it'll work.